properties. I won't prove them all, because most of these things, they exactly parallel the DTFT or, in a lot of cases, the Laplace transform property. But I do want to get through some. I did linearity quite a few. All right, I proved this one last time. I'm going to put some of these up. I proved it last time. This is all properties for the Z-trans. And we assume, of course, x of z is equal to the summation of n equals 0 to infinity, x of n times the z to the minus n. And here, z is equal to just rho, some value rho, times e to the j omega. And it parallels the similarities between the Laplace transform, z being analogous to the Laplace transform, and the DTFT being analogous to the Fourier transform. So that, again, the real benefit of the z is going to be in the ability to design and control more so than analyze. Remember that. But you got to get familiar with a lot of that. So that's the fundamental definition. And then last time I proved this one, x of n minus 1. This assumes we have x of n, and we know it's x of z. Well, for this one, and I'll just give you a tip, anytime you see n minus anything, that always means there's going to be a z to the minus anything. In this case, the minus anything is 1, so you always have z to the minus 1. Then it will be x of z here, but then you're going to add to it x of minus 1. And he has this outlined in your book. If you take a look there. Did you all see that, class? In your book, in the properties, if you look there, you can just turn to the page here. I'm gonna try to make sure that these properties. Do you remember us doing this one on Friday, proving? We actually went from the fundamental definition, and then what we did a variable change, right? And we went ahead and got that. Now, and then x to the n minus 2. Well, that's going to have a z to the minus 2. X of z, and then there's going to be a couple things. That's going to be plus x of minus 2, and plus, and this is just going to be plain old plus z to the minus 1, x of minus 1. Now I'm going to tell you, I don't expect you to know more than up to this point, but probably I'm going to give you some of these properties on an examination for one reason, because some of it gets a little confusing with these offsets, right, with the right shift and left shift. We can prove any of these you want, and I will if you want to. Now these are all left shifts. Then if we have an advance, or x of n plus 1, here, now we're going to get a z, x of z here, but then it'll be minus some stuff. Then it's going to be minus x of 0 times z, and x of n plus 2, I have some comments about this. Here you're going to get a z, you're going to get z squared x of z, and then it's minus x0 times z squared and minus x1 times z. Now I got 2 comments, really 3 comments on this one. All right, you can see the progression. In the book, he gives you, like, instead of n minus 1, n minus 2, he'll have it out there, n minus q, where q will be any value possible, and he'll have an extent of this thing. But here's what I want you to grab from this. Most of the time, when we deal with z-transforms, we deal with functions that have values that are non-zero only for n equals 0 and above. So x of minus 1, x of minus 2 are 0, almost always. Do you follow me on that one, class? The values for n less than 0 are usually not even considered for z-transforms, most of them. Which means x of minus 1 here would be 0. It means x of minus 2, x of minus 1 here would be 0. Follow me? Now this is a left shift. This is advancing everything to the left. These are the ones you encounter all the time. This right here, a shift to the, well actually you could call it a shift to the left or right, but something where you have an added number there instead of subtracted. This is moving things back in the opposite direction, which means now this is like an advancing, a function that advances. This isn't commonly encountered here, and you'll notice here you do have to worry about these added terms here and here. Follow me? These are the ones you worry about. This is usually, you don't worry about this stuff. It's just usually x of n minus 1 is z to the minus 1 here. X of n minus 2 is z to the minus 2 x of z. Follow me? And you usually don't have to worry about these. But here you do. However, this is not normally encountered, at least not a lot. They will ask you problems about it. It's not normally encountered. Follow me? As a matter of fact, well, I'll just leave it at that for now. Now, the next property that's important that you have to know, and I'm going through the properties because there's only about 4 transform pairs you need to know. Y'all remember what I said before? I said you have to know what? Delta of n, u of n, a to the n, u of n, right? Those. And then really delta of n minus anything, and that really is a transform property, but you need to know that one. Then from that point on, it's all using properties to get the transform pairs that we need and use. Got me on this? And you'll see the similarities between the DTFT and this, a lot of similarities. Now the next big property is if I have n times x of n, and I want to know this one. Almost your gut tells you there's a derivative in there, because if you've seen it with the Laplace transforms, right, and the DTFT. I'll just tell you how it comes about. If I go over here, you don't have to write this down, and I have x of z here equal to the summation n equals 0 to infinity, x of n times z to the minus n. Now I know instinctively I need to get an n x of n out here, so I have n x of n, right? The only way I can get that is taking the derivative of this with respect to z. Does everybody see how it'll pop out that minus n, everybody? If I take a derivative of this with respect to z, that's not a function of z right here. I get the minus n, z to the minus quantity n plus 1, right? So I'm going to go ahead and do it, just so you see it. Derivative of x of z with respect to z here gives me a summation, and now I get minus n x of n to the z minus quantity n plus 1 here, and still sum from 0 to infinity. Y'all give me that right there? Class? Now just watch this. What is z to the quantity n minus 1? Well, that would be what? That would be n equals 0 to infinity. That's really z to the minus n times z to the minus 1. So you can put z to the minus 1 here, and then you're going to have the summation, and you can put a minus sign out the front there. Summation of n x of n, right? Z to the minus n, right? Now this is what we want, isn't it, class? That is the z transform of n x of n, isn't it? Just look at the definition of the z transform. You notice now. So what do I need to do? There's a minus sign here too, to get this. Well, now I multiply both sides by a minus sign, makes that plus, and I multiply both sides by z. And when I do it, I get this. And you can see that that means this will give me minus z times the derivative with respect to z of x of z. And in fact, that is the transform pair. You all see that, class? I'm going to do it. Just give me a shot. Now, I'll do take it to the next, extend this. Instead of n, what if it's n squared x of n? How might you do this one? Just think about it logically. All right, I'm going to make a statement here. I know everybody is, this class has got smart people in it. You all agree that this right here can be represented as n times the quantity n x of n? Do you all agree with that? Mm-hmm. Do we have the transform for this? Right there, right? So what can we say? This really can be rendered as minus z times the derivative with respect to z of what? Of this. Do you agree with me? Right? It would be what? me say this again. This right here, minus z times derivative with respect to z of x of z. And you can go ahead and do that. All right, you can go ahead and do that. Derivative of z is just going to be 1 times this derivative plus this times the derivative of this, which would be a second derivative of x of z with respect to z. When all is said and done, what do you notice you get out of this one? Now you get a z squared, don't you? Take a look in the book, times the second derivative with respect to z of x of z, right? Plus z by itself times the first derivative of x of z with respect to z. Is that what the book has, your book? Can you do it? Y'all see this one in your book or not? Who has the properties open? Anybody? I'm trying to show, I don't know if they extend it out definitely, but this is n squared x of n.
Yeah.
Is that what they have? There's a lot of ways to write this. I like breaking it out. They might have left it in terms of a derivative, z times a derivative or something. Do they have this right here?
I don't know.
Well, that's a good one to write down. Huh? But really, what you get is just the derivative of that again, and you get it. The negative signs kill each other off. Follow me, class? All right, trying to show you a few of these. These are the properties that are meaningful. Now, another one that's useful you can run into from time to time. And I gotta say one other thing about this. A lot of the stuff that we're going through at a high rate of speed will all become the usefulness will be very apparent in your other classes. For instance, when you get digital image processing or digital signal processing, they're going to use a whole lot of this. When you get everybody here has to take, I think, controls, don't you? Dr. Hung's class? When you take that, he'll be using all this stuff for Laplace and Z-transform for stability work, but he'll go much further into detail, in depth about that. But this is your first exposure. You usually need to get exposed to important concepts at least 2 or 3 times in different courses before it really sinks in. And this is really your first one for the Z, but you'll get it quite a few other times. So the next one is where you get a to the n times x of n. Now, when you look at this, I can prove this, but it's going to be x of really z over a. Do you all remember back in the day when we were doing Laplace transforms, and if you had what? E to the AT, do you all remember what happens? It's basically the same thing. You'll notice there's not the scale of 1 over a out in front here. It's just x of a over z. I can prove that if you want. Do you see this in your book, by the way, class?
Is it A over Z or Z over A?
Z over a. Z over a. I'm sorry. Do you see it in your book or not? What page is it on the textbook? 3 what? 3-7? All right. That one's important. Now, I'll tell you one other thing about this. You can get this a lot. I can prove this. The easiest way to prove this, if you wanted to do it, go right to the definition of the Z-transform here, right? And if I have a to the n times this, couldn't I just take that, and if I have a to the n times that, it's like a to the minus n right there, isn't it, class? A to the plus n is like 1 over a to the minus n, correct? Now, can't you combine that and just make it z over a to the minus n? Can you all see that? And if you do that, you see the argument becomes z over a then, don't you, class? That's how it's done, without going into a lot of these proofs. It's that simple. So that one's useful. These are the ones that are really useful. The next set I'm about to put down. And I think you know what I'm going to put down, the modulation properties. They're a little different here. I can prove this. I think it suffices for me to just put it up, but I can't prove it. With modulation, I'm always thinking sine and cosine multipliers. We can do it for a more general form, and this is, by the way, the more general form, where a would be e to the j omega, all right, and you can break it up into, using Euler's either a cosine or a sine, we can define that in terms of that. But I'll just put this down. If you have x of n times cosine, I like to put omega naught in here, not leave it as omega, that goes down to, as you might guess, 1/2. But now it's going to be x. It won't be omega naught, or I mean omega minus omega naught. It's really just going to be z times e to the j omega naught. Now take note of that. It's z times this. Remember, z is defined as what? Rho times e to the j omega naught? Or this is e to the j omega, remember? So when you multiply this by that, you literally are adding that angle. It becomes the same thing as adding the angle. It's going to be that plus x of z times e to the minus j omega naught. In your book, do you see this? In your book, in your properties class? Pardon me?
No.
He does not have that one. Please write this down. This is a very, very powerful one and useful one. Then, if you have x of n times cosine of, sine of omega naught n, as you might gather, j over 2, but now it's going to be x of z e to the j omega naught right there, and then it's going to be minus x of z times e to the minus j omega naught. Now, you can see that this is the same type of modulation we had with the DTFT. Remember that? And the same basic form as what we had with what? Fourier, right? With Fourier transforms. The thing here, though, is now it's z times e to the j omega naught. That's a real important difference here. We can prove it if you want. We can get it using that right there. All right. Those two are important. Oh. This one's real important. I hope you put this, guys, can I get rid of this part here? These are in your tables, right? Just going to get rid of it. Then we're going to do some problems before we get into inverse Z and stuff. So now the next one is, what if I have the summation of x of n, or x of I, pardon me. I'm going to define this as x here of I. Write this one down. I equals 0 to n. I like calling this a new function. I'll call it y of n. And I want to find the transform of this. Now, does anybody remember doing this for the DTFT? We did this very same thing with the DTFT. And there was one thing I did that made everybody happy. Do you remember what it was? I bet you do. All right. Can't I write y of n equal to the summation of I equals 0 to n minus 1 of x of I, right? Plus x of n. I bet you now you get it. You all agree that that's legit, everyone? People? Come on. What am I going to do next? I know you know it. I know some of you know it. You don't want to say it. Anybody? All right, let me ask you this. You see what's going on. What is this right here? Look above it one line. Isn't that y of n minus 1? So now I have y of n equals y of n minus 1, right? Plus x of n. This assumes you know x of n goes to x of z. That's the assumption with all these. We know that relationship. What next? If I know x of n goes to x of z, then if I take the z transform of this, what do I get? Don't I get what? Y of z, right? Equal to, well, that's z to the minus 1 y of z, right? Minus what? Y of minus 1 plus x of z. Look at the property. Remember what I did? That's y of n minus 1, so I have to take z to the minus 1, y of z, right? Minus y of, or plus, pardon, plus y of minus 1, right? What is y of minus 1? Look at the definition of y. It's 0, isn't it? Because the sum starts at 0, right? So there is no minus 1. Do you follow me in this class? Everybody? That way we can get rid of this. Now, keep going. Look at this. I have y of z is equal to z to the minus 1 y of z plus x of z, or what do we see? We have y of z, right? Y of z times the quantity 1 minus z to the minus 1 is equal to x of z, or what is y of z? Just x of z divided by 1 minus z to the minus 1, isn't it, class? And that right here is this. This summation itself will give me x of z over 1 minus z to the minus 1. Now your book might have it slightly different. They might multiply top and bottom by z, and I'll see z over z minus 1, right, times the quantity x of z. Does your book have one of these two? Please look at the properties. Just take a look. It's real important what I'm showing you. I'm only highlighting the ones that are really important. You see it in your book? All right, that's summation. That's used all the time in digital signal processing. So this is one you're going to get all over and over again. And it's the same thing for the DTFT, only for the DTFT, instead of z, we have just e to the j omega. Don't we, class? It would be e to the minus j omega right there. Okay? This is going to be the z transform. Now, oh yeah. I'll erase this stuff too. All right, next, if we have x of n convolved with h of n, I can literally go ahead and I can do this for you. This isn't that bad of a deal to do convolution. I have to go ahead and define discrete time convolution and then take the z transform of it. But anybody want to just guess what it might be?
Multiplication? Yeah.
That's right. We can prove it if you want. It's not really an essential one. That's it. By the way, the definition of discrete time convolution that you're going to have to know, the definition of that from way back when, x of n convolved with h of n, that is a summation, right? And the summation is on I equals 0 to n, and it's going to be of here x of I times h, and then it's going to be n minus I. Remember, that's discrete time convolution. That is the definition of discrete time convolution that we've done. Unlike continuous time, where there's an integration, here it's a summation. In continuous time, we integrate it over tau, right? Here we sum over I. It's the difference. That we haven't used that in a while, but that is discrete time convolution. Follow me, class? You never really want to do that, unless that's a guns to your head. You always want to do it in the transform domain. You always want to take transform pairings and get it. All right? Mention one other one. There's an initial final value theorem. Now, I'll tell you the two. In my time, working all sorts of radar stuff, electromagnetic compatibility, any kind of problems with transient electromagnetics, and just about anything else I can think of, I've never had to do initial and final value theorem work. I'm just telling you that. However, if you get into the theoretical kind of work that can, in electromagnetics, I've done plenty of things like this, where there's solutions to functional forms of like a, have you all had electromagnetics 1 yet? No. Well, if you are taking it or have taken it, you're going to find out something where they have two equations that are called Maxwell's equations. It's really Michael Faraday's law of induction and Ampere's circle of current law that are combined to get one equation. But it uses a del squared operation, which is a second derivative spatially, and it has something where a differential equation appears that you have to use separation of variables to solve in 3 dimensions generally. That means is the forms of the solutions you get are often complicated mathematically. And oftentimes you're looking for the solution as something goes to infinity. For instance, distance r goes to infinity. So you have to use methods of figuring that out based on your knowledge of the special functions. But in the time domain, or in the discrete time domain, I have never had to worry about the initial final value theorems. So, that said, I'm really trying to say, if you really don't want to spend a lot of time on this, I understand why, because I never use it. You probably won't either, and I hope to gosh I don't get some nasty letter in the mail from somebody watching this, but that hasn't happened to me yet in one of these lectures, but I'm bracing for it. But I've never had to use it. However, you need to be aware of it. So when you talk about initial and final value, it's saying this. Suppose I know I have some x of n, this is what we know, and it went to some x of z. But here's what we're working with, was x of z. We don't know the x of n that caused it. So we're looking for x here of n when n goes to 0. And we want to take a look at what that value is. Now, the way I always tell people to do this is look at the fundamental definition of x of z. Let me put it here, I erased mine. So if I have x of z, that's equal to a summation here of n equals 0 to infinity of x of n times z to the minus n, right? Just take a look. That's the definition you have to know very well. Take a few terms of this. Isn't this equal to what? X of 0 times z to the 0 is 1, plus x of 1, right, times z to the minus 1, plus da-da-da-da-da, right? Now, if we want the initial value, how might we get this? Remember, all these terms after there are going to have something over a z, isn't it? The next term is x2 over z squared. The next one is x3 over z cubed, and so forth. Well, how would you get x of 0? How about we let z go to infinity? Wouldn't that do it, class? Sure it would, because then all those other terms would go away. And in fact, that's it. You just take the limit as, if you want the value of x of n equals 0, you just take the limit of x of z as z goes to infinity. And you get it. You got x of 0, the initial value. Follow me? Now, if you want the final value, you would do the same thing. Think about that whole series be written out. Now you want the value of x of n as it's going to infinity, right? How would you do that? Well, here's the old trick. You would take x of z, right? Multiply it by z minus 1. So then you're going to have this whole series with a z in front of it, minus that whole series by itself. And do y'all remember how all those terms canceled? Kept getting canceled, canceled, canceled. Do y'all remember that from that one trick I showed you? Until the last term, right? Well, in the book he shows us, I'm not going to do this one again for you, but if I want the final value, I mean, I can do it here, but it's kind of, I don't think it really is going to help your understanding. If you want x of n, and now as n goes to infinity, that's equal to the limit here as z goes to 1, not if 0, z goes to 1, of the quantity z minus 1 times x of z. Take a look in your book, see if he has this. This is the final value. Do you all see it? He should, I think.
Yes, he does.
It should be. Does he have z minus 1?
Yes.
And then times x of z as z goes to 1?
Mhm.
We can prove that if you want. It's the same old proof that we did before. All right? But that's a little, not really tricky. It's just z has to go to 1 for it to work. That's fine. But this one and this one, I have yet to use in a real engineering one. Now, please, if you're, don't send me a letter about this that you have. But I'm telling my class the truth. I haven't, so I don't really put a lot of focus and emphasis on this. You should be exposed to it and realize how you would get it if you had to get it. Now, Dr. Hung may have a whole world of things that he uses these theorems for that I don't. Because I don't generally use Z-transforms to do any kind of analysis where I'm looking at final or initial or final values of an actual data series. Here's the deal. In the real world where I work in, I've got the X series. I've got a sample data set. I know what it is. It's not obscure to me. If I want the first value, I look at the first value. If I want the final value, I look at the final value. It's not something that's not there for me to see. Follow me on that? That's the reason I don't worry that much about the abstractions like this. All right, now we get into, all right, did you have questions about the homework, anybody? Or not?
Yeah, I had one.
All right, give me a second, let me clear the board. Most of the ones I gave you the solutions, and they're very straightforward ones. But we'll do, I actually want to do a few. I wanted to do one other thing first, but that's okay. You know, when I was sitting where you're at, getting Z transforms and all that stuff, I kind of knew about Fourier what was valuable because I already had just a tad of exposure. And anybody that does any sound engineering, anybody who uses equalizers, that you can appreciate the frequency domain and the signal strength and power levels. But Z transforms were something I didn't see how to use them until graduate school, and you really start doing some design and analysis work where you're doing discrete time sampling. Most of the stuff we did, though, where a lot of this was valuable, was we had recorded data, and we wanted to do filter operations, and then based on that, we wanted to design systems that would be stable. All right, which one did you have?
2 to the n plus 1
Wait a second, 2 to the n plus 1.
times the cosine of 3n plus 4 times u to the n.
All right. For this one right here, let me tell you, I'm not over, am I? I got a whole bunch of people looking in at me.
No,
All right,
we have 134.
when you're doing this one, there's a couple ways to do it. One is, I'm going to just start with 2 to the n plus 1 times u of n. I want this, that's going to be my x of n that I'm going to use to multiply by the cosine. Follow me? Everybody class? Now when you do this right here, what do you get the transform of? Isn't this really what? That's 2, not z to the n. If you have, that's really equal to just what? 2, right? Times 2 to the n u of n. Isn't it, class? Think of it that way. You asked me about it, right? You all see what I'm doing? Taking 1 to 2's out in front. Right? Now when I do that, what do I know? That 2 comes over here, right? And what is 2 to the n u of n? Just, sorry, I put it,
Yeah.
sorry, 2 to the n u of n. Yeah, that's a to the n u of n, right? Well, that's just going to be what? A to the n u of n goes to, you want to do it that way, z over z minus 2. That's fine. You can do it that way. Do you agree with that? Go ahead.
So, okay, on the first one, that's z to the n plus 1 or 2?
Now, all of, it can't have a z in the time domain. That's 2 to the n plus 1. I'll make it clear. This is supposed to be 2 to the n plus 1, which is equal to 2 times 2 to the n u of n.
Okay.
That's all I did. Now, once I have this, 2 to the n plus 1 u of n goes to that. Now I can focus on this cosine business, right? Your book actually gives a transform of x of n, I think they do, maybe they don't, of cosine of like omega naught n plus some phase n, don't they, in the
Yeah.
properties? We can use that direct if you want, but we can also do it, we can say, if I want to take a look at the cosine, boy, I almost hate to do this to you, but let me just, give me a minute, give me 2 minutes, you don't have to write this down. If I take a look at cosine here of 3n plus 4, that's equal to 1/2, right, times e to the j quantity 3n plus 4 plus e to the minus j quantity 3n plus 4. And I can just break it down like that. And then I can go ahead and further break it down and say that's 1/2 times quantity e to the j4, some phase angle, times e to the j3n plus e to the minus j4 times e to the minus j3n. And again, I'm just ripping that apart, right? And then I look and I see that if I have just e, really this, I'll do it this way. If I have, boy, I almost feel like doing 8 of them, but here's what I'm going to say. I have this as really equal to 1/2 here times e to the j4 times, and I can make this, if you look at this is e to the 3j to the nth power plus e to the minus j4 times e to the minus j3 here to the nth power. In these two, this looks like an a to the n. You follow me on that, class? Now, we just did the thing, if you have a to the n, right, times x of n, that was really going to be x of what? Z over a. Y'all remember that, class? We just did that property, didn't we? Now look here. That means when I have e to the j3 here to the n times x of n, that is simply going to be x of z over e to the j3. If you look at this and follow my order of logic. Are you with me? Right? Now, just to follow, I just want to show you. This right here is the first one, times 1/2 times e to the j4, which is a simple constant, isn't it? E to the j4 over 2 is a simple constant, right? It's complex actually, but it's a constant. If I have that times this, and I look over here, this is like my x of n. Think of it this way. This is my x of n, right? Now I'm multiplying that times this cosine times u of n, right? Follow me? Well, one way to get it, since I have, this is x of n, if I have x of n times a to the n, I know that's going to be simply x of z over a. Specifically, when I have e to the j3 to the n times 2 times 2 to the n, u of n, times 1/2 times e to the j4. This goes to 1/2 e to the j, 1/2 e to the j4, right? Times, and then it's going to be this quantity, which will be 2 times z over a, or then it was going to be z over e to the j3 here, over, that's a z, pardon me, 2, that's a 2, over z over e to the j3 minus 2. That would be the first part when I took this and multiplied it times the x of n there, which is the 2 times 2 to the n times u of n. And then you would do the second part in the same way and you would add them. That's one way to get it. You follow what I'm doing here? I don't want to spend more time on this than I need to complete it. So you would have another term, only would be a minus j there. The second term, I could put that on there if you'd like. So you would have this, and then you would have plus 2, and it would be z over e to the minus j3 over z over e to the minus j3 minus 2. And you would just group those, and that would be a legitimate way to do this. It's a little more work, but it's legitimate. However, probably an easier way now, you can't use pure cosine modulation. The reason is because you got that added 4 there. But in the book, he does this. He says that what? If I have x of n times cosine of omega naught n plus a phase angle theta, that goes to what? 1/2, right? And then he has, take a look at your book. You see this one in your book? Doesn't he have x of n cosine in your book? In your book or not? I think I know what he does. He does this. He has this, doesn't he? A to the n cosine. Take a look at the pairs now. Look at the pairs. Do you see that one in your book? it'll have a to the n times cosine of omega naught n plus some phase angle or some constant.
He has that without the phase angle. And
He
the
sh-
only pairing with the phase angle he has is to absolute value of a to the n.
Times the absolute value.
So what he has is either that without the phase angle or a 2 in front absolute value of a to the n, like that.
Mm,
There's one that.
Can't we do it without the phase angle and
Property
then time
seven
shift?
doesn't have it.
Sure, you can do this real easy. Look, pardon me? I'm sorry, what? If you want to do, you can, I always like modulation. I like just you can break out cosine A plus B into a cosine term, cosine A, cosine B, right? And that's going to be what? Plus sine A, sine B, if you remember that. And you can go ahead and do that with modulation. But this specific one right here, this is the thing that causes a problem, that added phase angle. Now you can break it out into a cosine 3n times, what is it, cosine 4, plus sine 3n times sine 4, isn't that right? Cosine A plus B is cosine A, cosine B, plus sine A, sine B. Take a look at it. I believe I'm right, but I might be wrong. That's a trick you can use. I just do Euler's. I use Euler's on that one and just do it the way I was doing it. That'll be quicker, I think, in some ways. But you asked me if the phase angle isn't there. Somebody did? Who did? Didn't somebody ask me if the phase angle wasn't there?
I asked if you could just time shift it, or if you could just use it without the phase angle and time shift it, but the step function would make that.
Well, it's not quite that easy, and here's why. All right, if you look at this one, this is 2 to the n plus 1 here, but now it's cosine of 3 times the quantity. What would this be? N, take a look at this, plus what? 4 over 3, right? He chose that 4 for a reason. That is not an integer value. All right, now, if it was 2, it would be greater if it was 1.
Okay.
But that's 4/3, that's not an integer value. So it's not a simple right shift, left shift kind of deal. Are you with me on this, class? Because you have to have the 3 out in front of this, and it's times these two things, right? So you would have the 3 as a coefficient on a quantity, and that makes it a much different problem. Anyway, for this one right here, I thought in his book he had the cosine, go ahead.
Just wondering, could you just do the transformation he has and I don't know how to word it, because in 7 he has cosine of omega naught n plus a phase angle, and 6 he has the a to the n.
These are properties or pairings? Transform pairs?
Pairings. And properties he doesn't mention, like sine or cosine.
That's unfortunate, you should. I would recommend you do it with that. The way I was showing you, this is the answer, by the way, to that, the way I did it, where I broke it up. I broke up the cosine 3n plus 4 into its initial, using Euler's, I took 1/2 e to the j 3n plus 4 plus e to the j 3n minus 4, right? You can do it, and this is what you'll get. That's the right answer. The problem with that is it's in a kind of an ugly form. Now, you take 1 over these things, and it's going to be what? Z times e to the minus j3, z times e to the minus j3 minus 2. And this is going to be z times e to the plus j3 over z times e to the just plus j3 minus 2. You can multiply this times this downstairs and get a common denominator, and you can do a whole lot of condensing. But essentially, that's the right answer. And that's it right there. That's a brute force way to get it. Did you have another question about a problem?
I have a question about the last one, which is just u of n minus u of n minus 2.
All right, let's look at that.
And like, there is a second way to do it with like brackets, and I didn't
All right.
understand how to do that.
Give me the problem.
U of n minus u of n minus 2.
What does that look like? At n equals 0, it is 1, right? At n equal 1, you got 1 minus 0, right? It's 1, correct? At n equal 2, it is 0. N equal 3,
Sure.
N equal 4, go this way. This underscore means N equals 0, right? 0, 0, 0. There's only two values that are non-zero, aren't there? For N equals what? 0 and N equal 1, correct? Now, the easiest way to do this is go to the definition of Z transform. If I have values, 3 or 4 values like this, just go to the definition of the Z transform. I can go and I can do the Z transform of those two and subtract it. So just work with me on this, you'll see. X of Z for that one is going to be the summation X of N times Z to the minus N. Technically, N equals 0 to infinity. Just do it. N equals 0. I get 1 times Z to the 0 or 1, right? X equals 1. I get 1 times Z to the minus 1 or 1 over Z. That's it. There's nothing else. Every other value out here in this series, right, is 0. Follow me? So just 1 plus 1 over Z is the easiest way to do a Z transform of something that only has a couple of values, and say 3, 4 values, something like that. It's the easiest way. Can you all see that this is, you can write this any way you want, right? You can multiply this Z by Z and get Z plus 1 over Z. Doesn't matter. That's it. And does he have that?
Yeah, that's the answer.
Well, I mean, that's one way to get it from the fundamental definition. Another way is what? You could take the Z transform of that, which is what? Z over what? Z minus 1. Isn't that right? The Z transform of U to N. Take a look in your book if you don't believe it. Then you could subtract it from this, right? Well, that's Z over Z minus 1 times Z to the minus 2, right? And then you would subtract them and you would get that too, if you did it that way. Follow me? Either way you get it, but when there's just a few values, I go right to this thing right here. I go to the definition. I'm not going to play around with play games with all that other stuff.
1 minus Z to the negative 1.
What?
The answer to that one was 1 minus Z to the negative 1.
To this one? Wait, I mean, to,
The-
sorry. Wait. This is a, sorry. Let's see, we got, correct me on this, we got 1. Yeah, N equals 0, it's 1. N equals 1, it's 1. N equals 2, it's 0, right? That's 1 plus 1 over Z. Isn't that what he has? He might have this. He might have Z to the minus 1.
It was 1 minus Z to the negative 1. Because for some reason with the brackets they subtract.
I think there's something wrong. Is this his actual function, U of N minus U of N minus 2? Just look at the definition. You can't get more right than this. N equals 0, this is 1. Z to the 0 is 1, right? Plus, that's 1 and 2, right? Times Z to the minus 1, that's it. I think you might have made a mistake there.
Well, there's an earlier problem with brackets that also,
What do you say with brackets? What do you mean?
Yeah.
like the,
Does he have this? Does he have 1, 1, like that?
no, they have the little like squiggly brackets.
All right, well, yeah, where he has 1 and 1, and that's it?
One comma one.
That's,
Same thing.
yeah, like that? That's fine, but there's a bar under 1?
Yes, first one.
Do the math on it. There's no way it can't be that. Does he have anything else there? He has 1 minus Z to the minus 1?
I'm looking through, I think what he did in the part A solution where he used the properties, I think he did some simplification wrong and then just used that answer as the answer.
For this one, it's going to be Z over Z minus 1. It's minus the quantity, and this one is going to be Z over Z minus 1 here, but it's going to be times Z to the minus 2 right there.
Correct.
All right, now if you do that, you factor out the Z over Z minus 1, and you get 1 minus 1 over Z squared, right? Then if you break it out, it still comes to 1 over Z minus 1. I mean, 1 1 plus 1 over z. Just check that. All right. Amount of time. All right, I'll tell you what I'm going to, I think if you looked at those problems I gave you, they're all doable, very easily doable by the properties. What I'm going to do next time is I'm going to give you some reading, and we're going to go to inverse Z transforms. Here's really what I want to focus my attention on. Doing Z transforms that are meaningful to do based on systems. I'm going to look at block diagrams, show you how to develop Z, the actual overall Z, H of Z, the actual system transfer function, the Z domain. Find out how you can get the time domain response using an inverse Z transform. Now, I'll give you a few more things to work on in some reading, but what I hope to do by Friday is have us to the point where now we can look at real systems with Z transform analysis, like we did with Laplace. Remember Laplace, we used op-amps and stuff to build circuits that realize real H of S's and stuff like this? That's where I'm going with this. But there will be digital circuits, so we're going to have adders, subtractors, and delay circuits. Those are real digital things that you've had. You know how a delay circuit works, you have clocks, you know how to add values, right, and things like that. I didn't realize the time flew so fast. All right, guys, see you.